Hey guys, this is a video I'm creating as sort of a test to see how the recording works and whether or not a very long video will store properly and process quickly and so on. So I'm going to go over chapter 0, which are the prerequisite materials. Let me try to share my screen here. Okay, so chapter 0 is a little review chapter that's going to help you guys remember the stuff from Algebra 1 and Algebra 2.
Teachers at this time, if you would, please use the email list of 10th grade students to identify those who have completed the device agreement form on Skyward. If you have a student on the 10th grade list who needs the device, please send them to the comments at this time. Students, please have a seat in the comments when you arrive. Thank you.
Okay, so also I'm testing the audio, making sure you guys can hear me, and so on. So chapter 0, part 1 is about number sets and set notation. So in Algebra 1, typically you would have one and only one solution to a given problem. 2x plus 5 equals 7, x equals 1. However, in Algebra 2, late in Algebra 1, and also in Algebra 2 in the higher mathematics, you've probably encountered problems that had multiple solutions. We call that a number set. So in analyzing a problem, if more than one solution is possible, you'll have a set of numbers that solves that problem. So we're going to work with sets a lot. Some things to know: subset means includes only numbers that are in a larger set. So in this scenario, if B is a subset of A, I write that like so. That little sideways U looks almost like a C. Let me make that a little more distinct, because that looks too much like a C. Kind of like that. So that means B is a subset of A, and every element of B is included in A. Try to get the camera right here. Okay, so is an element of means if you've got 3, let's say, and that's an element of set A, you use this character, it's a Greek letter, to indicate 3 is an element of set A. The universal set is every possible value. For a given situation. So if we're talking about, I don't know, pin numbers, and that would be 0 through 9. If we're talking about license plates, that would be 0 through 9 and also A through Z, and also a dash, because license plates have a dash in there. So the complement of a set is every element that is in the universal set, but not in a given set. So every element in the universal set but not in a given set. So if I want the complement of A, I would look at the universal set, and everything that's not in A but is in the universal set would be A's complement. And that's written like this. A with a little tick mark means the complement of A. So the union of two sets is written like this. Got that U, A union B. This means every element in A or B. And that or is the key word here. Intersection, when we take the intersection of two sets, we use this N kind of looking symbol, and it's every element in A and B. So the key word here is and. We'll do some examples to reinforce this, so don't worry if that's not completely clear to you just yet. Okay, now let's talk about some number sets that are used so often that we have a special symbol for them. So first of all, the complex number set. That's every number, including imaginary numbers, that you've ever heard of. Every number is a complex number. A subset of the complex number are the real numbers. So they have no imaginary part. And then the reals are broken up into two main subsets. The rationals, so these can be expressed as a fraction, and the irrationals, these cannot be expressed as a fraction. So this would be like 17, negative 22, 4 over 5. This would be like pi or e or the square root of 2. Now integers are a subset of the rationals that have no fractional part. So they are negative 25, negative 17, 0, 1, 2, 3, and so on. Numbers that have no fractional part, positive or negative. Now the wholes are a subset of the integers, and they start with 0. So they are ascending from 0, 0, 1, 2, 3, 4. And then the naturals do not include 0. Now you might think that's a pretty subtle distinction between these last two sets, and it is, but it's important for some higher order mathematics to include or exclude 0 in certain scenarios. Okay, so in this graph, and you'll find this in your book, is a visual Venn diagram of complex numbers, real, imaginary, rational, irrational, and so on. So this might help you understand it. Okay, so let's identify the sets to which a number belongs. First of all, 17. Well, it is a complex number, of course, so that goes without saying. And then it's also a real number. And sometimes with imaginary numbers, they use I, and irrationals, they use H. So I'm pretty sure that's what this text does. So I could, in some texts, I've seen it used for irrationals, but I'm going to use H for irrationals here because I will be the imaginary numbers. Okay, so it is also real. It is also rational. It is also whole. And it is also, well, got those out of order. So integer, then whole, then natural. So that's all the sets it belongs to. The square root of 3 is complex. It is real because it includes no imaginary part. And it is irrational because it is a non-repeating, non-terminating decimal. And as a consequence, cannot be expressed as a fraction. 1.2, complex, real, rational, but is it an integer? No, because it has a fractional part. Okay, -1, complex, real, rational, and then integer, but is it a whole? No, because remember, wholes start at 0 and are ascending. And then pi, well, it's complex, it's real, there's no imaginary part, and then it's irrational. Non-repeating, non-terminating decimal can never be expressed as a fraction, no matter how big you make the denominator. All right, and now example F here, 2 plus 6i. It is complex and imaginary. It does include the I value. It is an imaginary, has an imaginary part, and so it is an imaginary number. Okay, so let's do some work with sets. Let U equal this. So this is our universal set in this scenario. Set A is going to be elements 1, 2, 3, and 4. Set B is going to be elements 7 and 9. So let's find A union B. In other words, every element that's in either A or B. So that's going to be 1, 2, 3, 4, 7, and 9. So that's every element that's in either A or B. And then B intersection A. So now we want to find every element that is in B and is also in A. In this case, they share nothing. And so the intersection is going to be the empty or the null set. In other words, a set with no elements. You could also use the no solution symbol. Okay, but this is a better answer for the purposes of chapter 0. All right, A complement. So this is going to be every element that's in the universal set, but not in A. So that's going to be 0, 1 is represented, 2 is represented, 3 is, 4 is, 5 is not, and then 6, 7, 8, and 9. So this is A's complement. Every element in the universal set, but not in A. B's complement. Well, 0, 1, 2, 3, 4, 5, 6, not 7 because 7 is represented, and 8. And not 9 again because 9 is there. So this is B's complement. So that's how you find the union, the intersection, and the complement of a set. Okay, so here are some problems, and if you want to pause the video here and try these, that can reinforce what we're talking about. All right, chapter 0, part 2, operations with complex numbers. So here's the guy from Big Bang using a pickup line. Pretty cool. All right, complex numbers. Powers of I. There are 4 possible answers when I'm taking I to a power. So if I take...
Teacher, please use the email list of 9th grade students. Identify those who have completed the device agreement form on Skyward. If you have a student on the 9th grade list, please send them the comments at this time. Students, please have a seat in the comments when you arrive. Thank you.
So if we have I to the 0 power, anything to the 0 power is 1. Any value, no matter what it is. If I take it to the 0 power, the result is 1. If I take anything to the first power, the answer is itself. Now, I is the square root of -1. So that's the definition of I. So if I square I squared, it's going to be the square root of -1 squared. So that's going to be -1. And then I to the third power. Remember your rules of exponents? So that's like I squared times I. That's going to be -I. And you'll find these 4 answers repeat over and over. So I to the 4th power, we're back to 1. I to the 5th power, we're back to I. I to the 6th power, we're back to -1. I to the 7th power, we're back to -I. So you see how these 4 answers will repeat over and over and over again. So a quick way to find any power of I is through what's called modular arithmetic. Sounds complicated, but it's not. It's in fact pretty simple. So if I had I to the 23rd power, for example, I want to divide this by 4 because there are 4 possible answers, and then find the remainder. Whatever that remainder is, I compare it with this first set of 4, and it will give us the answer. So I to the 23rd power, if I divide 23 by 4, I find that it's 5 times 4 is 20, and that leaves us with the remainder of 3. So I come over here, and I know that this is the same as I to the 3rd power, because the remainder is 3, and so it's -I. Now be careful using your TI calculator to find these high powers of I, because for whatever reason, it's sort of a quirk in the software, it will often give you a little mathematical artifact. So it might say like -I plus 0.00001 or something like that. Anyway, it's much easier to find these by hand. So this is a situation where you can rely on your brain more than you can on your calculator. Okay, so let's add, subtract, and multiply complex numbers. First of all, when we add these, we're going to find the like terms. So the 2 real parts are 5 and -2. And the 2 imaginary parts are negative 3i plus 4i. And addition is both commutative and associative. In other words, I can move these around and regroup them however I like. And so I've done so here. I've moved the real terms together and the imaginary terms together. 5 plus negative 2 is 3. Negative 3 plus 4 is positive 1. And so 3 plus 1i, or 3 plus I, is the answer. Okay, so subtracting. We're going to use an old trick you probably learned in elementary school: keep, change, change. So I keep the first imaginary number the same, change the symbol to addition, and then change the sign of both parts of the second imaginary number. So keep, change, change. Now it's just like the first problem. 5 plus negative 4, negative 7i plus 4i. And that's 1 minus 3i. Your calculator can do these. So you can do these by calculator, but so far the examples haven't been complex enough to really justify the use of a calculator. But your I button on your calculator is if you hit the second symbol and then the period. So hit second and then period on your TI calculator to get the I, and you just put it in exactly like you see here. And usually your calculator is right, but again, high powers of I, it can give you a mathematical artifact. Okay, now let's do part C, which is multiplying complex numbers. So we're going to use the old FOIL trick. First times first, outer times outer, inner times inner, and then last times last. So FOIL. It's a way to multiply two binomials. How many wheels in a bicycle? 2. How many terms in a binomial? 2. So if you're multiplying two binomials, two numbers that have two parts, you can use the FOIL method like so. All right, negative 10 plus 20i. Negative times a negative is positive, plus 6i. And then negative times a positive here is going to be negative 12i squared. I times I is I squared. And remember from that previous section, I squared is negative 1. So it's important that we change I squared wherever we find it to negative 1. So this is negative 10 plus 26i. I'm going to combine these two terms to get 26i plus 12. Negative times a negative is positive. So this is 2 plus 26i, like so. Okay, moving on. Using complex conjugates. So when we divide complex numbers like so, we often want to realize the denominator. Now, you're probably familiar with rationalizing the denominator, but here we realize the denominator. In other words, we make it a real number. So similar principle. We're going to multiply top and bottom by the complex conjugate of the denominator. So you take the denominator and change the sign between the real and imaginary part. That's it. And that's the conjugate. Now here I'm going to use a calculator to save us some time. So in the calculator, I'm going to type 5 plus 3i in parentheses times 1 plus 2i, also in parentheses. Don't forget your parentheses. TI-83 loves parentheses. And the answer is negative 1 plus 13i. And this is kind of interesting. Because I use the conjugate, the denominator should be a real number. So we're going to do 1 minus 2i in parentheses times 1 plus 2i, also in parentheses. And the answer is 5. So there we go. We have used complex conjugates to realize the denominator. And if you want to write this in standard form, which sometimes the text might ask you for, that's going to look like this. Just break it up into two parts. Okay, moving on. Here are also some problems. If you want to reinforce what we've learned, pause the video here, try to work through these. All right, quadratic functions. So there are four ways to solve a quadratic. Quadratics look like this. This part has to be there. The a value cannot be 0. So in other words, it has to have something times a variable squared to be a quadratic. The standard form looks like this: ax squared plus bx plus c. B and c can be 0, a cannot. So it has to have an x squared part or some variable squared. So parts of a quadratic. Intercepts are where it touches, and I say it, but I should say where the graph and axis, and that is the x or the y axis. X-intercepts are typically what we would be more interested in, but often the y axis means something too. Axis of symmetry. So this is a vertical line about which the graph is symmetric. Okay, so I'm going to give you a little visual here. So in this case, you've got the two x-intercepts and the y-intercept. And then if I had this quadratic, the dotted line would approximate the axis of symmetry, the vertical line about which the graph is symmetric. So a vertex is going to occur at x equals negative b over 2a, and then the function evaluated at negative b over 2a. So that's the point where it will occur. Negative b over 2a from the formula ax squared plus bx plus c is going to be the x-coordinate of your vertex, and then the function evaluated at that x value will be the y-coordinate of your vertex. And it will always be a max or a min. In other words, a highest or a lowest point. And a max or a min, the next definition, of course, highest or lowest point for the graph, depending on the orientation of the quadratic. Domain and range. So the domain for a quadratic, as I have described it here, is always going to be all real numbers. So I'm just going to say x is an element of the real number set, using some of that set notation I taught you earlier. So x is an element of the real numbers, describes the domain. The range, however, you're going to have a couple scenarios. If it goes up, then it's going to be y is greater than or equal to the function evaluated at negative b over 2a. So that y-coordinate of the vertex. And if it goes downward, it's going to be y is less than or equal to that y-coordinate of the vertex. Okay. So there are four methods for solving a quadratic. Again, the first and easiest is graphing. And this is a method you'll use your calculator for. So let me try to share my calculator window here. All right, hopefully that worked. So to solve a quadratic by graphing, I would go to y equals, clear out whatever mess you've got in there. And we're going to input whatever ax squared plus bx plus c looks like in this particular case. So let's do x squared plus 5x plus 6. If I graph this, well, my window's weird, so I'm going to zoom and then 6 to give me the standard window, and I see two x-intercepts. So identifying those two x-intercepts, I see they occur at -3 and -2. So that's solving by graphing. Now let me go back to the other screen. Okay, so you're going to use your calculator to graph, and we did that for the problem f of x equals x squared plus 5x plus 6. And we got a graph that looks something like that, and we see that x equals -3 and -2 are our solutions. Okay, so the next method is going to be by factoring. So let's use the same problem. Y equals x squared plus 5x plus 6. So there are two sort of factoring techniques you'll use. And the first one and easiest one is when you have no a value, or your a value is 1. So if it is just x squared, not 5x squared, not -2x squared, just x squared, then you can set y equal to 0 and create this little template, because you're interested where y is 0. That's where the x-intercepts occur. And then I'm looking for, I'm going to put x here and here. I'm looking for two numbers that add up to 5 and multiply together to make 6. So just to be clear, m plus n needs to equal the b value, which in this case is 5. And m times n needs to equal the c value, which is 6. So that's going to be +2 and +3. Now I'm going to use the zero product property, or ZPP. So zero product property says if two things multiplied together equal 0, then one of them or the other must equal 0. Because the only way to get 0 as a product is if one or the other thing is 0. One of the two factors is 0. So ZPP allows us to do this. If I solve this, I'll get the same two answers I got from graphing, like so. So that's factoring. There's a more complex method of factoring that we'll get into later in late in chapter 1 and then also in chapter 2. But for now, just remember that factoring is a way to solve a quadratic. Next, we have completing the square. There we go. So completing the square. Making sure this meeting is still going here, because it sounded like something crashed. Yeah, it's still going. Okay. So completing the square is a pretty complicated way to solve a quadratic, but it's one that has a lot of important uses in developing formulas, and we're going to use it quite a bit later on in the book, so it is something we need to know. Completing the square. So let's use y equals x squared plus 4x minus 7. So we want to find the solution of the x-intercepts for this, if they exist, or the imaginary solutions if no real solutions exist. Now that's one advantage. The first two methods will not find imaginary solutions, but completing the square and then the fourth method I'm going to show you will. All right, so the first thing you want to do is set y equal to 0, because we're interested where y is 0. That's the x-intercept. And now we want to take this constant term and we want to move it over to the other side of the equation. So I'm going to make this, if I add 7 to each side, then that's going to give me 7 equals x squared plus 4x. And then I'm going to make a little blank here because I want to, on both sides actually, because I want to complete the square. So in order to complete the square, I'm going to take the b value and divide it by 2 and then square it. And in this case, that's 4, so I need to add 4 to each side. Now the result on this right is a perfect square trinomial. In other words, it's a plus b squared. So I get 11 equals, if I factor that, it's x plus 2 squared. So the perfect square trinomial. And just to help you guys remember, that's a squared plus 2ab plus b squared. And it's always going to factor to a plus b squared. So that's how I got from here, x squared plus 4x plus 4 to x plus 2 squared. I use this shortcut over here, and I want to change the font color. So let's make that red. So you know that's kind of an aside. Okay, so from here we're going to use the square root property, which tells me, I'm going to go to red again, that if x squared equals n, then x equals plus or minus the square root of n. So using that property, I get this. Now if I subtract 2 from each side, I get this. So that's an irrational solution, one that we could not have found by the first 2 methods, but completing the square finds it pretty easily. And it also will find imaginary solutions. And finally, the 4th method for solving a quadratic is the quadratic formula, the granddaddy of all. So the quadratic formula tells us that if ax squared plus bx plus c equals 0, in other words, we've got a quadratic equation, we're trying to find its x-intercepts or its zeros. We can set x equal to negative b plus or minus the square root of b squared minus 4ac over 2a, and solve it by this method. So let's solve the same one we did for for method 3 here. X squared plus 4x minus 7. So a value is 1, b value is 4, c value is negative 7, and we just plug those in. So x equals negative 4 plus or minus the square root. 4 squared is 16 minus 4 times 1 times negative 7. So that's going to be a negative 28. Let's see, 4 times a times negative 7. Just checking something real quick here. Okay, so it's going to be over 2 times 8, which is just 2. So x is going to equal negative 2 plus or minus the square root of 16 minus a negative 28. So let's see, that's going to be 16 plus 28, which is 38 plus 6, which is 44 over 2. All right, now x equals negative 2. I'm sorry. I don't know where I got negative 2 from. It should be negative 4. My apologies. Okay, now it's right. So negative 4 plus or minus, and then the square root of 44, I'm going to break this radical down. So the first thing you want to do is factor out any perfect squares. And I know 4 is a perfect square. And 4 times 11 is 44. So I can make this into the square root of 4 times the square root of 11. So x equals negative 4 plus or minus the square root of 4 is 2 over the square root of 11 over 2. And now if I divide both of these by 2, x equals -2 plus or minus the square root of 11. And once again, we get the same solution we did before using this different method. So those are the 4 ways to solve a quadratic. All right, once again, some problems you may want to work through. You can pause here and do that if you like. Reinforce what you just learned. The odd answers are in the back of the book, by the way, so always check those. And then the last section that we're going to talk about in this video is 0 part 4, which is nth roots. Now, you used to square roots. Square roots find the second root of a number, but there are other roots. We call them nth roots, and they could be cubic roots, and they could be fourth roots, fifth roots, and so on. But in general, if I have a radical form, let's say I've got the third root of 2 to the 4th power, I can rewrite that as a rational exponent. So that's also 2 to the 4/3. So that's an important relationship to make note of. These are interchangeable ways to express nth roots. They both mean the same thing, in other words. Okay, so some properties of exponents and roots. First of all, exponents. You've got the product of powers. So you just add the exponents, and I'm talking about this first one here. And then the second one is the quotient of powers. You subtract the exponents. And then the third property of exponents is the power of a power. You multiply the exponents. And the fourth property of exponents is a power of a product. You're going to distribute that power to both of the factors, like you see here on 4. The fifth one, you got the power of a quotient. Once again, you'll distribute that power to the numerator and denominator. And then the sixth property of exponents, you've got a quotient to a negative power. So you will invert the numerator and denominator in this case. If you have a negative power, you're going to flip the ratio, like you see here. And then a couple, and you'll remember those from Algebra 2, probably Algebra 1 as well. And then you got some roots here. So let's see, we've got, if we multiply powers of, or we multiply 2 roots with the same index, in other words, this n value is the same, we can combine them into one root, like you see here. And then the one we've already discussed, which is I can write something in radical form or in rational exponent form. Okay, so feel free to review other resources on that, because that was a lot to review really quickly. And it's probably been a while since you've seen that, but don't worry, the applications will help reinforce all that stuff. Okay, so let's talk about some examples. First of all, this negative symbol tells us something. So when I'm talking about a root, a square root, that means it has an even index, even being 2, 4, 6, 8, and so on. So in this case, it's understood to be 2. That's an even indexed root, meaning it can have a positive and a negative. So if I have the square root of n, that means the positive root in general, or the principal root. If I have negative square root of n, that's the negative root. And then if I have plus or minus the square root of n, that's both. So normally you'll run into one of these 3 representations. In this case, we want the negative root, and so that's -7. Now, this b value is an odd index. It has an index of 3. So the ambiguity is gone. It's either going to be positive or negative. It's not going to be either or. It's just going to be one or the other. It's not going to be or. It's going to be either. Yeah, there we go. Okay, so this can only be positive. So we're going to use some of those properties of roots, and we're going to break this up into the third root of 64 over the third root of 27. The third root of 64 is 4, and the third root of 27 is 3. So this is positive 4/3. Now this last one, they try to trick us a little bit. the fourth root of negative 121. So 4 is an even value. We have an even index. We have a negative radicand. That has no real solution. That would have only an imaginary solution. So no real solution when you have an even index and a negative radicand. That's what's under the radical symbol. Okay, so one kind of funky, exotic situation is an even, odd situation where you have an even index, an even power on the radicand, and then an odd resultant power. If you have this scenario, you have to put it in absolute values. And a lot of people miss this question on the first test because they leave off the absolute values. Even, odd means I place the answer in absolute values if I'm simplifying a rational exponent or a radical situation like this. Even, odd is when you apply this. Okay, so the sixth root of n to the 18th power, I'm going to rewrite this as n to the 18 over 6, which reduces to n to the third. However, even index, even power on the radicand, odd resultant power. And so I need to put it in absolute values. Now the fourth root of 81 times the fourth root of a plus 1 to the 12th power. I'm going to break it up into two parts using that property of roots that we discussed earlier. The fourth root of 81 is 3. Now, I don't expect you to have all these memorized like I do. I've worked these problems out many times, and so I know a lot of this stuff by heart. You would use a calculator. You can put in 81 to the 1/4 power is a convenient way to find the fourth root of 81. It's going to tell you 3. So this is going to be a plus 1 to the 12 over 4. So that's 3 times a plus 1 to the third power. So even, odd, I need to put this whole mess again in absolute values. Now, C will not reduce in a traditional sense because 63 is not a perfect square and y cubed is not a perfect square. So I need to factor out any perfect squares. So let's bring this problem down here and let's talk about 63. I need to figure out what the factorization of 63 is just to ensure that it does not have a perfect square factor. So that's going to be any two numbers that multiply together to make 63 will give us a good start. So let's see, 31 and 3. What's up, my dude?
Are you doing online?
Mm-hmm. Well, I'm just making a video.
Oh, okay. Well, that looks really good. I thought you were just doing math for fun.
No, I'm just doing a video. Sorry. That's okay, dude. Okay, so 31 times 3. Now, 31 is a prime. Does it break down further? 3 is a prime. Does it break down further? Neither one of these are perfect squares, so we can't reduce the 63 part. However, excuse me, the y cubed part, I can rewrite as y squared times y. And y squared is a perfect square. So I can rewrite this as the square root of 63 times the square root of y squared times the square root of y, breaking up all those parts. Radical 63 times y, even, odd, and then times the square root of y. Now, this isn't even, odd, but the original formulation was odd under the radical. So actually, this is not a case where you would use absolute values. So the even, odd only applies to the original representation. So if we go up here, the problem as it was originally written is even, odd. So no absolute values are necessary in this case. And I'm going to simplify this answer to y times the square root of 63y. Like so. And then D is in delta. Let me bring that down here. We've got some more room. Okay. So fifth root of negative p to the 10th. So this is this negative is going to introduce an imaginary part. So before we just said no real solution, this time let's go ahead and figure out what the imaginary solution would be. So this is the fifth root of -1 times the fifth root of p to the 10th times the fifth root of q to the 7th. Well, actually, we're not sure if that's going to be positive or negative. So the final answer won't include an imaginary like I originally thought. All right, 5, fifth root of -1, we cannot simplify. Well, actually, yeah, we can. Because the fifth root of -1 is -1. You put that in your calculator. All right, and then the fifth root of p to the 10th power is going to be p to the 10 over 5, which is p squared. Odd, even, no need for absolute values here. And then the fifth root of q to the 7th, that's a little more complicated. So it does have a perfect power of 5. So that's the fifth root of q to the 5th times the fifth root of q squared, kind of running out of room there. So fifth root of q to the 5th, fifth root of q squared, and so that's just going to be q times the fifth root of q squared. And then, so that's negative p squared q times the fifth root of q squared, like so. Now, those are really complicated. And you saw even I kind of stumbled a little bit here because there's so many rules to remember. There's so many things to consider when you're fooling around with these problems. You have to be pretty meticulous when you're working these complex radical simplifications. So be patient with yourself and with me. We'll get through it. And so they kind of throw this in. It doesn't necessarily fit. It's sort of shoehorned into this section. But the depreciation formula. So this formula represents how things devalue over time or increase in value if the rate is positive. But in this case, it's a depreciation. So in this formula, the A is the amount at time t. The P is the original amount, in this case, that something was worth. The R is the rate of depreciation as a decimal. And then the T is the time that has passed. So boats are one of the things that people buy that has the highest percentage of buyer regret. In other words, people wish they hadn't bought it because it depreciates so quickly. The values decrease. So it depreciates at around 8% per year. If you buy a new boat for $10,000, what will be its approximate value in 7 years? So the A, the amount of time t, is going to be the P. So that's 10,000 times 1 minus, and then 8% as a decimal, 0.08, and then to the 7th power. So 10,000 times 0.92 to the 7th power. I'm going to use my calculator here just to save some time. So typing in the calculator, 10,000 times 0.92 to the 7th power. And I get 5578.46. And it's 47 if I round to the nearest cent, which we'll go ahead and do. And I'll use the approximately equal to symbol to indicate that we have rounded or approximated the answer. So it's going to lose almost half its value in that 7 years. Okay, so this is an assignment I would normally give for Chapter 0. I'm not going to give it for this one. Feel free to look through these problems if you have an interest, but it's not something I'm going to collect. Thank you, guys.